as well. Let's move to the next presentation. The next presentation is by Amir. Amir is an algorithms and software engineering with more than 10 years of experience in leading complex multidisciplinary technological projects. And since joining Innoviz in the early days in 2016, Amir has been responsible for the company's product's low-level algorithms, and he just moved up to develop the company's perception software from scratch. Nowadays, Amir oversees Innoviz perception solutions from data collection through algorithms development. With that, I'd like to welcome Amir, and you can take over.
Hey, so thank you for the introduction. And today I'm going to speak of one of the biggest challenges Innoviz currently has when it comes to our perception stack. And maybe surprisingly, it's not going to be algorithms that I'm going to discuss. Actually, I'm going to discuss the data pipeline at Innoviz and how we manage and control a huge data set and evaluate them for better product. So I'll quickly share my screen. Yeah. So I think it makes sense to start off with the description of Innoviz operational system. Innoviz LiDAR, the InnovizOne, is mounted at the front of the vehicle. And like every LiDAR, it outputs point cloud. And then the point cloud is being processed in Innoviz ECU, which is responsible for the perception and the connectivity with the car over the AutoSAR domain. But when we try to collect data, we want to make sure the system is really scalable, so we can deploy it easily on multiple cars. And another thing which is really important is to make sure that the data collection system is as decoupled as possible from the platform itself. Because Innoviz has multiple cars around the world, and the odds, and multiple cars from multiple types, and the odds to deploy a system with the OEM on the same car type that we currently have is slim. So in order to achieve this, we added some more sensors to data collection system. We added camera. The camera is mostly for annotation purposes, because still humans are feeling more comfortable with the RGB image versus point clouds. But we do some more with this camera, and I'll explain later. Secondly, we add GPS system. And the reason why we add a GPS system as a localization system and not tapping to the car odometry is exactly this decouple that we want to achieve between the perception system and the car itself. Finally, we record data using a proprietary software that just runs on PC, usual PC. This software is controlling and monitoring the data collection system, and also doing time sync between the different sensors. And lastly, we have a really modest storage that is enough for a few days of recording. So what we don't have in this system, we don't have an expensive loggers, which you often can see around when it comes to autonomous vehicle data collection system. And we don't have any fancy time sync between different sensors. We're doing everything on software. So this setup is really cheap and easy to deploy on multiple platforms around the world. Okay, so now I'm going to get a little bit deeper into Innoviz data pipeline. So the first thing you want to look at is the different data source that Innoviz uses, which I think really common to any other autonomous vehicle perception company. So Innoviz Fleet is an important data source, but it's not the only one. Innoviz is tier 2, which means Innoviz sells the LiDAR and perception to a tier 1, which ends up selling the entire system to the OEM, to the car maker. And Innoviz partners are really important data source due to two reasons. One, The capacity for data collection is really huge, usually with these tier 2, with these tier 1s. And secondly, they tend to collect the data on the target platform, which is really important for the validation of the software. Lastly, here is the simulation. So here you can see InnovizOne simulation derived by Cognata, which is our simulation partner. People tend to favor simulation in order to increase the capacity, but actually Innoviz is using the simulation not only to increase the capacity, but also to evaluate really safety critical scenarios. As you can see here, the odds to spot a pedestrian on a freeway is really slim, let alone getting into a situation of almost incident with a pedestrian. So for this safety critical scenario, evaluation and optimization, simulation is really important as we find it. So as you can probably imagine, this variety of data source tends to come with different formats. Now, if we want to have an efficient data pipeline system, we have two major options. One is developing different APIs for each data source, for each data format, or converting all these data formats into a single data format and only invest in a single API. So as the requirements from this API is really challenging, we require random access, really low latency, high throughput. We decided to do the conversion and convert all the different data formats into a single one and invest only on single API. So this is the post-processing. Next thing we do is we tag the data. We take the data for sampling purposes, which I'll describe later. And how we do it, we just collect all the available data sources that we have on the car and adding map and weather services in order to understand the road infrastructure condition, like static objects we have on the road, like bridges, tunnels, road incline, and obviously also querying for the weather condition in the specific drive. And obviously, when developing a safety critical system for autonomous vehicle, being able to operate on multiple weather conditions is really important and critical for the success of the entire program. So after collecting the signals from the car, like position dynamics, map and weather services, we also collecting or tagging the data using the perception system and the LiDAR system outputs. It means that we keep most of the objects that are being detected by the perception system and some of the telemetries outputted by the LiDAR. For instance, temperature, blockade system, errors, whatever the LiDAR outputs. By combining all this raw tagging and adding really a thin layer of logic, we can derive what we call insights. We can understand if the car now is in traffic jam condition, if it's in safety scenario, if it's changing lanes. So by even by having really modest car setup, we're still able to do really good, I would say, deep tagging of the data that is recorded. Lastly, in this raw data processing stage, we have visual inspection. We find it really important to have actual people looking and sampling the data, make sure everything is intact. In spite everything is automated and tested, still errors and changes might occur, and it's really affecting the next phases of the data pipeline. Errors and bad data, which is being collected in these early stages, is really affecting greatly throughout the pipeline until it's been detected as faulty sample. This is why here visual inspection and QA are really important. Okay, so now we have the data ready and canonized in Innoviz accepted formats. And next thing is to label data, to annotate the data. So before going deeply into the stage, I'll just say that we use a lot of not annotated data, but still annotation and labeling is a key element both for algorithm optimization and testing and verification of the performance. The most vanilla way to sample data is just random sampling. It means taking sample every now and then from the available data set. But actually this strategy is good to start off with. But as the perception system and the entire system is getting better and better, it's really hard to find effective samples, I would say, samples which are challenging the algorithms or the system. So we still use this approach mostly for testing purposes, just to make sure the coverage is still good, but we tend to prefer different approaches. Next approach, as I described before, is using the tagging system and look for interest areas. Look for traffic jam conditions, safety scenarios, changing lanes, regions in the world that you've never been in. Really make sure you sample the data from places which you want to be optimized on. I think one of the most interesting sampling approach is what most people know as active learning. So the base idea behind active learning is sampling data points which will benefit the target algorithm the most. It's and if it can be done automatically, it's also a huge plus. So how we do this active learning? So we start off by training our target detector or target system over the available data set. In parallel, we develop a reference detector, which is a detector that is hopefully has minimal or very low correlation with the target detector, or it has an unfair advantage. Like using the future in order to take decision on the present. Obviously, this is not something you can do on the target platform. And examples for minimal correlation is using cross-domain and using camera image in order to detect objects. So now we have the target detector and we have a reference system. So what we do is we're taking the unlabeled data available and we run both detector over this unlabeled data. So now we have two streams of data. So usually these two streams are matched. Every object that is found on the target detector is also found on the reference detector. But sometimes you get mismatches. And this mismatches tends to be important to the target detector's improvement. So we feed these disagreements between the two data streams, we feed them through the annotation, and we add them to the dev set. And this cycle goes over and over again. So if you get everything automated, except from the annotation, which is partially automated, you can improve the algorithms without any research done, active research done on the target detector. One thing to mention is that it's also possible to build an efficient active learning system without any reference detector. If the target detector is outputting confidence that actually makes sense, so you can just sample frames in which the confidence was low or marginal. And these samples tends also to be really effective for the target detector to get better. So the team can stay focused on the target detector, but still build a relatively efficient active learning system. One last comment is that active learning is not only good for deep learning algorithms. Also for classical algorithms, active learning or active sampling of data is effective. For instance, in this image on the right, you can see Innoviz point classification feature. Actually, it just classified each point on the point cloud and says if it's drivable or obstacle. So if you know what is the driving path of the vehicle, you can safely assume that you don't have the static objects which might endanger the car itself. So you can also use this as an active learning system or active sampling system and sample the samples that you actually have issue with. Okay, so now we have the data sampled and ready for annotation. And how we do annotation is also something I'd like to share. So Innoviz has in-house annotation team and in-house annotation tool. And the reason why we believe this ability is critical is because still today 3D annotation is not trivial, and each sensor and each feature has its own issues and problems. And actually, if you can optimize the annotation process in-house with annotation experts, which are really close to the algorithm team and the testing team, then outputting this task to a third party will be much more efficient. So we have this internal annotation team, which are mostly doing QA and like these special tasks. But the majority of the data is being transmitted or moved to our annotation partners, which are doing this annotation at scale after our internal annotation team has instructed them on how to do this annotation. The next approach is not using any manual annotation at all and just annotate everything automatically. So this approach can really increase the capacity of the annotation and can really generate huge amount of annotated data, but obviously the quality is not always enough. And we do this in similar ways as I shared before in the active learning or active sampling process. Again, in this station or in this phase, we also have manual quality assurance, both for the auto annotation process and the external vendors. Again, adding faulty samples in these stages is really costly. So really invest on quality assurance and verification of this process. So now everything is ready for the algorithms, but still, I think it's important to make sure that all this system is being orchestrated, controlled, and monitored in a single place. So we have this web dashboard for control and monitoring this full pipeline. And with this dashboard, we can do QA, we can dispatch tasks, we can move annotation tasks to our vendors and get them back. We can do root cause analysis, which I'll describe later, and many other features or tasks. Okay, next thing you want to do, you want to obviously optimize the algorithms. So with Innoviz is doing perception. So obviously deep learning is a key element, and we use deep learning and data-driven approach quite often. But actually point clouds opens the door for classical models. And classical models tend to be much more predictable. And sometimes in this autonomous vehicle space, this is important to have a baseline which is predictable. So the algo team is querying the database and taking the data which is relevant for a given task. For instance, if you want to improve on traffic jams, then you can use samples which are tagged as traffic jams. If we want to see pedestrians, then we can query for frames which holds pedestrians, etc. And the algo team is optimizing on the given tasks. After the algo team is happy with the results, the algo team releases an algo release. Algo release can be viewed as a golden model for the deployed version of Innoviz perception. This is end-to-end perception stack, which outputs the full perception results for a given recording. So this algo release is being evaluated on a bigger data set, and just to make sure everything is intact, all the other features has the same KPIs, the agreed KPIs, and the feature that was under development is being improved. So after a few cycles, the algo release is ready, and then it's moved to the embedded team in order to deploy the algorithm. So the embedded team takes this algo release and runs it in parallel to the target platform, which is also being fed with a given recording from the database. So we have these two streams, one on the algo release, the next one on the embedded release. And the algo release not only outputs the end results, but also outputs intermediate results of every important calculation. So the embedded team can match the results between the target release and the algo release and make sure everything is equivalent. Now, sometimes in this process, the algo team took a decision which is not optimal and not optimal for the embedded design or the target platform. So there we have two options. One is the embedded team saying the algo is communicating this issue to the algo team, and the algo team is fixing. But sometimes the embedded team can fix it on their own. For instance, if the algo team has a calculation which is not optimal for the acceleration that's available on the target platform, then the embedded team can change the algo team code and make sure it yields the same results, and then backport the change back to the algo release or back to the algo team. And then this cycle goes once again. So after a few iterations, usually the CV app is released for the final stage, which is model testing. If up until now we did evaluation on relatively small data set, now for this full testing for release, we need to increase the data set a lot. So if you want to have an efficient storage, you just cannot keep the entire results or all the artifacts from both CV release, the target release, and the algo release. So we find it really efficient to do this online evaluation. It means that every frame which is outputted, both in the algo release and the embedded release, is being evaluated in real time, like online. And we only keep the statistics and places of disagreement either between the CV app and the algo or between the results and the ground truth. So now we have like this huge run and huge statistics and failures. Everything is, again, is tagged in the database. And because it's tagged in the database, we can generate reports which are which describing the current state, and also we can track past runs and past version performance versus the new one. And the next phase is root cause analysis of issues. The root cause analysis, this entire step, this root cause analysis and visualization, is a completely different tool chain, which is really interesting, but we won't get deeply into it today. But I just say that the same web dashboard is used by the defect manager in order to select the interesting failures, which we need to root cause deeply. And this entire system also uses automatic root cause analysis tooling in order to screen already known root cause. And here you can see just a small example of one of our visualization tooling. What you can see here, this is low confidence evaluation. And what we want to make sure, we don't have any critical false positives. As you can see, this red one is a critical false positive. But actually, if you look deeply into it, you understand this is just an association problem between two different detectors we have on the system. So this is a software bug. And we found out this visualization is really critical and makes all this root cause analysis really effective. So just to summarize, Innoviz is doing a lot of algorithms, and our product eventually is an algorithmic pipeline. But we kind of finding ourselves investing more and more in all the infrastructure that is actually driving this data pipeline and driving the algorithms and give access to the data for either algorithm improvement or data validation. And not just giving access to the data, but actually flag the data samples, which are the most critical. Because evaluating thousands of hours of recording is not something that you can do just as is. You need to make sure you know what samples actually makes the difference. So with this, I'm going to give just a quick company interview and then take questions if there are any. So Innoviz was founded 5 years ago and announced InnovizOne, which is this LiDAR. You can see fairly small device, automotive grade LiDAR, which is now being manufactured in scale. Along the way, Innoviz partnered with multiple tier ones and got a design win with BMW, which is a leading car makers, as probably all of you know. And Innoviz will supply InnovizOne LiDAR and Innoviz Perception for BMW L3 program. And lastly, Innoviz announced Innoviz2, which is even a lower cost, improved performance version of InnovizOne. So what makes Innoviz different? So Innoviz is the only LiDAR maker which has a serious production contract with OEM, with the car maker. Innoviz has fully automated and up-to-speed production and supply chain. And Innoviz LiDAR cost is derived by multiple architectural decision that actually makes it possible, like developing the full chipset of the system in-house and sticking to the 905 nanometers, which is really helping to reduce the cost. So to finish off with, I'll show a few videos and examples for InnovizOne. So actually, I really like this mobile camera captures videos, because then the audience can be sure there are no tricks involved. So you can see here just a casual highway drive, and you can get sense of Innoviz LiDAR resolution, field of view, range, sensitivity, and quality in general. Lastly, here you can see some examples that, and kind of matches between LiDAR and camera. So you can get sense of why it's important to have redundancy to camera. And here you can see just direct sun out of tunnel scenario. You can see the camera is completely blinded, and the LiDAR is still operating pretty well. Same on rainy conditions and during night. So this again can give you a sense why LiDAR redundancy is important. This is my talk. Hopefully you are this will inspire you to invest more on data management, data accessibility, and data pipeline, and not only stick to the algorithms optimization.
Thank you for the talk, Amir. Unfortunately, we are far over time, so I'm going to have to skip the discussion. But if somebody has questions, then please post them on the chat, and Amir can probably reply on the chat directly. Thanks again, Amir.